This will be lecture 34. Now that we have done the 6 very simple 3D point groups just based on a single rotation axis, now we can fold in ones that are based on the rules that we set up with the Euler's uh, um, uh, construction. You recall is having, sorry about the slope here, it should be straight axes if in space, where I'm going to imagine a pole that I have. I'm going to take a object, rotate it about alpha, then I'm going to take that object, there's another axis here, which is B, and I'm going to rotate that one beta. So it's going to swing all the way around, let's say to some other point here. And what that means is that this original one is related to this one by some rotation about another axis here, C gamma, which would relate, this one to that one. So, and this is what's required, of course, because the motifs have to be all self-consistent. I can't be generating them around and keep on filling space forever with non-closed sets of symmetry operations, right? So these operations have to eventually fold back on themselves, which is always why we have, here's operation 1, here's operation 2, and then, actually I should have shown, this is position 1, this is position 2, this is position 3, and then that means that this has to be related to this one through some self-consistent third operation, which here is rotation because we haven't used mirror planes, it hasn't flipped. And so that limits, that's one of those things, for example, that limits what you can do in 3 dimensions, right? Because there's only so many ways that this is going to actually work. And we derived a set of equations to make that work. And they're shown here on the left side. We first had our spherical triangle. And, we have, remember how this is related to a pole that came down here and intercepted this sphere. Actually, let me show it penetrating through the sphere just to make that clear. And then we had another one here coming up and penetrating the sphere here. And then, of course, that's related in our thesis to a third axis, C. Well, I mean, I'm not spinning them yet. So without spinning them, right, we had A, B, and C poles defining the spherical triangle, and we just labeled these things as the one opposite the B pole is B, the one opposite there is A, and the one opposite there is C. So the way to think about this is that this is the spherical solid angle that is the angle between the A and the C axis. C is the between A and B axis, and A is the angle between the B and C axis. And we showed you that basically there's a law of cosine for this. Now we showed you how you could build a polar triangle for this and said, well, this BC, for example, is formed by a great circle on this sphere. And if I drew a pole perpendicular to BC, it would come out there and it defines a polar spherical triangle. And that had this kind of unique property where, the edges of that polar triangle are 180 minus the internal angle here. And the reason we're talking about internal angles there is that we introduced the idea, well, not only do I have a spherical triangle, but we're going to do rotations around this pole of alpha, this pole of beta, and this pole of gamma. And there's another construction that we just presented to you that showed, we didn't derive it, but basically that the internal angle here, this is gamma over 2, this ends up being alpha over 2, this one's equal to beta over 2. And going back to what we were saying about the polar triangle, we found out that 180 minus, gamma over 2 and the three sides are such that you can insert those into the law of cosines for the spherical triangle. And that's how you get these expressions. They're very, you can tell they look very similar to the original um, law of cosines for spherical triangle. But when you put in 1 minus an angle, of course, it changes the cosine sine expression a little bit. And that's why this looks different. And that it's kind of important to tell you that trick in order to get a set of equations then that actually you can plug in for alpha over 2, gamma over 2, beta over 2, and derive what the angles between the axes are if you're going to have these rotations, right? So essentially all that work we did was to reduce this to the number of variables, so that if we say, for example, I'm going to have a twofold axis here, so beta is going to equal 180, alpha is going to equal 180. You know, what are all the possibilities for gamma? And the reason we're doing this one, of course, with insight ahead of time, instead of just running through this and finding out all the times it doesn't work, we're telling you that, you know, intuitively, you know, that if there's twofold axis, you can have a third one that's a twofold axis, very Cartesian. That's just one solution though here. So we said, all right, let's have twofold axes and see how many other axes we can create. And because we know there's actually a few solutions there, we put n here because there's going to be the ability to do 2, 2, 2. Another thing that'll work will be 3, 2, 2, although you won't have unique twofold axes, and so it'll be 3, 2. And then you have 4, 2, 2, and 6, 2, 2, etc. So this is a very viable one because these equations give you lots of solutions. And we're telling you that ahead of time. You could take that table we did last time and just simply have a computer program which cranks through all of these, finding the solutions, just that we're going to tell you ahead of time. And having you go through that exercise is probably not that useful. So, so that's where we are. Now we're going to use these. And yeah, so just wanted to point out before we do that, A, remember, is the angle between B and C. So the procedure here will be like, all right, I want to start with two twofold axes, right? That's what we mean by this 2 and 2. So let's say A and B. So beta and alpha are going to be 180 because twofold axis is 180 rotation. And then we're going to ask, all right, well, if we just do that, what's A, B, and C? And it turns out that the reason there's a solution here is that when we plug in beta over 2, right, would be 180 over 2. Alpha over 2 would be 180 over 2. And you can see here, this is going to be solved, this is going to be solved. It turns out that because these are 0 and stuff like that, you kill these off, and cosine A, cosine B equals 0, which means they're 90 degrees. So it's telling you that A and B, right, are 90 degrees, which says that the way this is going to look is that the angle between B and C axis is 90 degrees always in the solution, and the angle between A and C is always 90 degrees in solution. So I can show you that here, which I wrote over right now. But so if you plug in for alpha and beta, just like I was saying, you arrive at cosine A. You should do this exercise just to make sure you understand it. Because at first when you look at this, you say, oh, I don't have gamma over 2 yet. And we don't. What will happen is you'll see here the reason this ends up being a viable n, where we can think of this thing as n, is that this ends up being 0, this ends up being 0. Again, that means that A and B, because the cosine of something equals 0 means it's 90 degrees. So this means all the solutions have this. Whatever C is, let's imagine it right here going straight up. It says that A, if we call this axis A, is always 90 degrees, as long as this is a twofold axis. And it says that this is 90 degrees. That's a twofold axis. right? What we don't know yet is what rotations here are compatible. That's going to be gamma with all this. And we don't know this, which is the angle between the A and B axis, which is C. So with solving these first two equations, I have this picture now. With the last equation, when you solve for it, you get cosine C equals cosine of gamma over 2. Of course, I can just do the inverse of cosine each one of those. You find out that C equals gamma over 2. So what that means for n over here, since gamma is just, so for example, if I say it's a 222, gamma is 180, right? So the relationship there, remember, is that if I say n equals 2, what I mean there is that gamma equals 180, right? So basically 360 divided by n equals gamma, right? So if I have, for example, a gamma of 180, because I want to make C now a twofold axis, right? Well, this says that the angle between these guys will be 90, right? So in other words, I say gamma is going to be 180 because it's going to be twofold axis. So I'm going to force this to be gamma because I want to see what that solution is. That's my n equals 2. And what it tells me is that this is going to be 90 degrees. So I end up with Cartesian axes, right? And you can see that done out in a complete way in the next view graph. So I'm going to look at the specific case now of where I've said n equals 2. And remember I told you that means then that 360 divided by n, which is gamma, right? So gamma divided by 2 says that C is going to 90 degrees, just like I told you. And so that means that all of these angles between the axes are mutual 90 degrees, right? They're all 90 degrees away from each other. So if we look and see what that looks like, it's shown here. So remember, the trick is always to draw things that don't have too much symmetry, right? So here, I wouldn't mistakenly make a square because I didn't have any fourfold axes, right? So I want to make it as generic as possible, and there's no reason that this width should be this width or whatever. This is why we drew it this way, because we don't want to add any extra symmetry where we don't have it. So if you imagine since these axes are perpendicular to each other, if I want to draw a simple shape here that represents it, sort of like a Wigner sights, except I don't have any, exact distance of half of along any axes, I'll just draw a plane perpendicular to this rotational axis, this one, and this one, and it defines this as long as I make sure that I'm not making any of these edges equal for some reason, because I don't have any criterion that says they should be equal. Just that this symmetry is kind of then the minimum symmetry that I described just with these perpendicular twofold axes. And so now you can also see that this works, because let's imagine I have, when you have these shapes created this way, you can create your motifs on one face. So let's say, remember, from an operation point of view, we said we're going to do A pi. Now we're going to operate on that with B pi, and that's going to equal C pi, right? So that's our little operation equation, right? So A is first. So rotate around A pi, that's going to put this thing over here like that, right? So I've rotated 180 degrees if I drew that correctly. Not bad. I'd say it's pretty good. So then I operate on that. So this was 1. This is 2. Then I operate on that with B pi, which brings this guy up here. So this is position 3. And then we can say, are 1 and 3 related to each other through a rotation? And indeed, they're related by the C pi axis. So you can see our equations are correct. They're making everything work out just fine. Now we can go back to our little representation and draw that on C22. And now you can see what I was talking about before in the last lecture. You can see how on the other side of the globe now I have an open one that says it's down. So this is up, and then this is down, right? And so think about a sphere, and there's an axis that goes back here, right? And so this spins about this twofold axis right here, right? That's why when I look at the symmetry element, I have that twofold axis over, that's the C axis, right? So again, this is just creating a symmetry element, a volume that represents the symmetry of these axes, and I just showed you how it works with a simple motif. But the way that this is represented is to build a sphere and say, all right, when I look at the axes in 3 dimensions coming out of this globe, how are the symmetry elements arranged? So this would be, for example, in the way that I've drawn it, maybe this is, A pi coming out, and this was C pi coming up, and this was, B pi coming out this way. But of course, they go through the globe onto the other side, and so you have you draw these things on the other side because you could be looking at the sphere this way versus this way. So this sphere, no matter how you turn it, if you imagine turning it in your head, you're seeing these symmetry elements on the surface of that globe always, moving as you turn the sphere. So anyway, this twofold axis here takes this element that was on the up side of the sphere and it puts it in the back, right? So that's that, and vice versa here. Here, this element's on the surface, and there's like this guy that goes here and through this rotation axis, and that goes onto the back side, right? And of course, it's all self-consistent with B. We don't need to draw any more motifs because if I look at B, B goes through here, and what that twofold axis does is takes this on the sphere. On the back side of the sphere, if we rotate backwards, you can imagine this thing going up over as I rotate, and it ends up on the other side of the sphere, right? So just picture if you were to, this is your eye, if you were to look down this way, right, and I rotate to the left 180 degrees, you'd put this on the back side, and you'd have that motif, right? So that's consistent. And if I look at the front, right, this is the easiest one, the front one, right, that's consistent because I just rotate this about here and I get that, right? So this little motif pattern does indeed represent, in a way, the motif where the symmetry elements are represented on the right side. And that is 2, 2, 2.